we are going to continue with our study of chi-squared tests by looking at 2x2 contingency tables. So in a random sample of 1,000 people, it is found that 7% have a liver ailment. Of those who have a liver ailment, 90% are drinkers, those who drink alcohol. And of those who do not have a liver ailment, 80% are drinkers. So you might remember this data set when we were studying it in Math 350 and we were talking about conditional probabilities. Okay, so let's try to fill in this information. There's 1,000 people. 7% have a liver ailment, so that's 70. So 930 do not have a liver ailment. Okay, and then of those who have a liver ailment, 90% are drinkers, people who drink alcohol. So 90% of 70 is 63. Okay, so that means there are 7 who do not drink. And then 80% of those who do not have a liver ailment are drinkers. So 80% of 930 is 744. And that means there's 186 people left over who do not drink. Okay, so we can say that there are 807 people who drink, and there's 193 people who do not drink. And the question that we want to answer is liver disease correlated with drinking? And by correlated, I mean, does liver disease depend on whether you drink or not? And this is an example of, again, categorical data. This is data that can be divided into categories. It's a little bit different than what we did last time. Instead of there being 4 categories of blood type, here we have 2 variables. We have drinking or non-drinking, and then we have liver disease or no liver disease. So we have 2 variables and 2 categories. This is called a 2x2 contingency table. That's a table that shows the dependence of one variable with 2 categories on another variable with 2 categories. So let's look at the conditional probabilities that we probably computed last semester. Amongst the drinkers, what is the proportion that have liver disease? Well, we saw that there were 807 people who drink and that 63% of them have liver disease. So that gives us 7.81%. What about the probability of people who have liver disease given that they're non-drinkers? Okay, well, there were 7 people who had liver disease that were non-drinkers, and there were 193 total people that were non-drinkers. And so this gave us a total of 3.63%. And the question is, are these probabilities significantly different? You'll notice that the probability of having liver disease doubles if you're a drinker versus if you're a non-drinker. Okay, does that mean it's significant? Well, we're going to have to conduct a test. Something to note that the drinking does double the probability. Okay, so our hypotheses are that the null hypothesis is that the probability of having liver disease, given that you're a drinker, would be equal to the probability of having liver disease given you're a non-drinker. That is the simplest explanation where nothing interesting happens. That there's just one probability of liver disease and that it does not depend on whether you're a drinker or a non-drinker. Okay, so these would be essentially the same thing as just the probability of liver disease. Well, what that means is that if the probability of liver disease given drinking is equal to the probability of liver disease given non-drinking, then liver disease and drinking are independent. They're independent random variables. Okay, so then the alternative is that the probability of liver disease given you're a drinker is not equal to the probability of liver disease given you're a non-drinker. And that would mean that liver disease was somehow dependent on drinking status. Okay, so let's talk a little bit about these contingency tables, add some terminology for you. Okay, so the categories that define drinking and liver disease status are what we call dichotomous. Okay, so you either have liver disease or you don't. You can't be in both. And you either drink alcohol or you don't. You can't be in both categories. The things that you see within the 2x2 table, so these numbers here within the 2x2 table, okay, we're going to call those the joint frequencies. And then the row and column totals we'll call the marginal frequencies. And that should relate to the idea of marginal probabilities that we looked at back in Math 350 last semester. Okay? So, for example, for the row marginals, we had 70. We have 70 people with liver disease. And we had 930 without. For the column marginals, we have that 807 people are drinkers and 193 are non-drinkers. Okay, and then the 1,000, we call that the grand total. That's the sum of the row or the column marginals. So the question we want to answer is, to start is, what would the table look like if the proportions with and without liver disease were equally distributed amongst those who do and do not drink? So what would the null hypothesis table look like? So what we're going to do is we're going to compute what I'm going to call the expected frequencies, which is the joint frequencies that would agree with the null hypothesis. Okay, so in order to do this, I'm going to talk about first, what is the proportion that have liver disease? So here in our sample, 70 out of 1,000 people have liver disease, or 7%. So suppose that the proportion with liver disease were equal for both drinkers and non-drinkers. Okay, then the null hypothesis would be true, right? So we'd have a proportion of drinkers would be 7%, and the proportion of non-drinkers that have liver disease would be 7%. What would that look like? So we could take the 807 drinkers, and we could multiply that by 70 over 1,000. That's the probability of having liver disease. Okay, and then that gives us an expected frequency of 56.49. Okay, so we would expect that if 7% of drinkers had liver disease, then there should have been 56.49 drinkers with liver disease. But if we took the non-drinkers, okay, so that's 193, and then we multiplied that by 70 over 1,000, then we would expect that 13.51 of the non-drinkers should have had liver disease. Okay, not just the 7 that we had. Okay, so that's if we think about it as the proportion that have liver disease is 7%. What if we just think about the proportion of drinkers? Okay, so there are 807 drinkers out of 1,000. So we expect there to be 80.7% of people being drinkers. Now suppose that the proportion of drinkers were equal for those with and without liver disease. Okay, so that would mean that 80% of those with liver disease drink and 80% of those without liver disease drink. What would that look like? Well, we would take the 70. Those are the number of people with liver disease, and then 80%, or 807 out of 1,000 of them, are supposed to have liver disease. So that would have again given us 56.49. Or we could have taken the 930 people without liver disease. 80% of those should have been drinkers, if the null hypothesis was true, and that would have given us 750.51. And so what I want you to notice is a pattern that's gone on here when I found the expected frequency. 807 was the column marginal, the column total, and then 70, that was the row total, and I multiplied those together and then divided by 1,000 to get me the expected frequency. Okay, 193 was a column total. And then I multiplied by the row total of 70 divided by 1,000, that gave me the expected frequency. Similarly, 930 was a row total, and I can multiply by the column total, 807, divided by 1,000, and that gave me 750.51. So this gives us a sense of how to compute the expected frequencies. The expected frequencies for a contingency table are E sub ij, where you take the row I total, and you multiply by the column j total, and then you divide that whole thing by the grand total. So we saw that if we took 70 times 807 divided by 1,000, we got 56.49. If we took 7d times 193 and divided by 1,000, we got 13.51. Okay, and then after we've filled those two in, we can just see that we would have to add 750.51 for the total to be 807. And then in the second column, we would have to add 179.49 in order for the sum of those two columns to be, or rows to be 193. Okay. So now we have observed frequencies and expected frequencies. And so what we're going to do is we're going to define a new chi-squared test. The chi-squared test is going to be, we want to take the observed frequencies, call them OIJ, minus the expected frequencies, EIJ. We're going to square those, and then we're going to divide by EIJ. Those are the expected frequencies. We're going to sum over the two rows and the two columns. Now, the number of degrees of freedom in this case is going to be 1. Now you say to yourself, why is the number of degrees of freedom going to be 1? Well, last time we saw the number of degrees of freedom was really the number of independent variables that we had. So the question is how many independent variables do we have here? Well, once you determine the number of drinkers with liver disease, okay, 63, okay, or the expected 56.49, then you can determine all of the other three variables. I have to add 7 to 63 to get 70. I have to add 744 to 63 to get 807. And of course, once I've determined 63, 744, and 7, then I can use either the row total or the column total to tell me that the last one has to be 186. So essentially, once I have this number, the number of drinkers with liver disease, 63, then the other three are determined if I know the row and column totals. So there's really only one independent frequency and in this problem. So we call the degrees of freedom in this case 1. Okay, so let's use this table and let's compute the chi-square statistic. So the chi-square statistic is going to be 63 minus 56.49 squared over 56.49. So I wanted you to see that first one. I've taken the expected frequency of 63, or sorry, the observed frequency of 63, subtracted the expected of 56.49, squared that and divided by 56.49. We can do 7 minus 13.51 squared over 13.51. We have 744 minus 750.51 squared over 750.51. And then finally, we have 186 minus 179.49 squared over 179.49. Now, what does that mean? Well, the chi-square, if we add all those up, that's going to be 4.1797. Okay, and so we need to compute the rejection region, okay, for 0.05. So we want our chi-square to be bigger than chi 0.05. So we should look at our chi-squared table. Our degrees of freedom is 1, so we're going to look at the top row of this table, okay? And we're going to see that our rejection region was, for 0.05, was we needed chi-squared to be bigger than 3.84. And in fact, it was 4.1797, okay? So we can say that our p-value is somewhere between 0.025 and 0.05. Okay. So here our rejection region was that the chi-squared had to be bigger than 3.84. Okay, and we can see that our p-value, we said, was between 0.025 and 0.5. Okay, notice that our rejection region is one-sided, it's directional, so we're not doing anything like doubling any probabilities or anything. If you used R, you could get that the p-value is 0.041. So using alpha equals 0.05, we're going to reject the null hypothesis. Okay, the probability of having liver disease, given that you're a drinker, okay, probability of having liver disease given you're a drinker is not equal to the probability of having a liver disease given you're a non-drinker. Okay, so we suspect here, or we have evidence to suggest that liver disease depends on whether you drink or not. Okay, and then we would have to add some sort of biological explanation. Okay, why is drinking affect the liver? Okay, because we can't just assume that this correlation that we have gives us a causal relationship. Okay, now let's talk about, now that we've done this example, what these experiments look like. Okay, so when you're viewing a chi-square contingency table, a 2x2, the data has to be viewed in one of two ways. One is that you have a categorical variable with two random samples. And in this case, you could think about, okay, let's say we have two groups. Okay, one's given a drug. The other is a placebo. And then we're going to measure the disease. Okay, so you either have the disease or you don't, or maybe your disease condition improves or it doesn't. Okay, and so you can view this using a 2x2 contingency table. Okay, you have the drug group, the control group, or the placebo group. Okay, either the disease condition is improving or it is not. Okay, and then you can do a chi-square test. Or you can have two categorical variables, okay, with one random sample. An example of this is you can have one group, so one giant group, and then maybe you could separate them into by two different categories. So we could separate them, say, by hair or eye color. Okay, so we can have a group of people, and then we have those who have a dark hair color and a light hair color, and then those who have a dark eye color and a light eye color. And that can be a 2x2 contingency table. Now, the distinction between these two ideas is not so clear. So which case does the liver data fall within? You can think about it as we took one group of people and they either have liver disease and they don't, or they have, or they drink or they don't. Or you can think about it as two groups of people. We have a group of people who drink, a group of people who don't drink, and they either have liver disease or they don't. Okay, so liver disease you can think about kind of in both categories. Now, in order to apply the chi-square test, all observations within a sample must be independent of each other. Okay, so we can't take people from the same family. Okay, and there's other constraints when you're doing biology experiments to make sure that your samples are independent. You're not taking samples from the same plants. Okay, you're using different plants when you're doing your samples, something like that. Something that's interesting with sample size is that the expected frequency of each observation has to be at least 5. Okay, and then a small p-value can only imply a causal relationship if the data arise from an experiment with a randomized assignment of treatments. Otherwise, we can only infer that the observation association is not due to chance. Okay, so just because you find a small p-value does not necessarily mean you have that dependence relationship. Okay, it depends on how you designed your experiment. If you have randomly assigned people into a drug group and a placebo group, okay, then you're going to be able to make a causal conclusion. Okay, if I randomly surveyed people and they either drink or don't drink, then I might be able to make some conclusions about liver disease.